Today what we're going to look on is kind of a combination of two different topics, neither of which is a full class. We're going to look at visualization, and we're going to look at network analysis. And I'm sure all of you have done some of both of these. I'm going to try to show you a sort of journalistic approach to these topics. In particular, the frame we're going to use is visualization as perception. I like to think of visualization as a sort of hack that interfaces with the human visual system. And I'm going to try to show you sort of start from that perspective and build upward from it. And then we're going to do social networks, and I'm going to throw in a certain amount of social network theory, meaning we're going to talk about sociological ideas, which is ultimately why we do social network analysis. And then we're going to show some examples of network analysis actually being done in journalism, including some research that I did just surveying how it's used. This is a list of the relationship between various topics in a book called Gödel, Escher, Bach, which is this sort of early book on cognitive science and artificial intelligence and art, and won a Pulitzer Prize in 1980. If I wanted to ask you if infinity is connected to the halting problem, you would have to sit here and do quite a lot of sort of back and forth searching, looking at all the things that infinity is connected to and then scanning through this list. It would take you quite a long time to try to look at those connections. If I show the same information like this, then it's trivial to answer that question, or to answer more transitive questions, right? Is infinity connected to Turing? This, I think, is a more interesting fact than it seems. So why should the exact same information displayed in this way be so much more useful for answering certain types of questions? Anybody got a theory of what's going on here?
Well, the ability to read came a lot later in our evolution than like assessing spatial relationships between things.
All right, so there's the idea of spatial relationships, yeah. Anyone else got a thought here?
One keyword appear like multiple times, so it is much more easier if one keyword appear once and then the connection goes to different items.
Uh-huh, yep.
You have them in relation to each other and the whole picture, like all the relationships. So that makes it much easier to understand.
Yeah. There's something about putting this in visual form as opposed to just words that it makes a big difference. And my friend Tamara Munzner, who wrote a wonderful book that's just called Visualization, puts it this way: carefully designed images as a form of external memory. So here's a very interesting fact. Let's throw some words on a board. I'm going to use my usual cat, Matt. Some colors. Okay. I want everybody to focus here. So I want you to literally look at my finger. This is actually important for this to work. And then I want you to tell me what this word is. Can you see it while you're staring here? It's too bad. You already read it. Damn it. Let's try this on the slide here. All right, look here. What's this word? All right. So I'm trying to demonstrate two things. One is that your field of view where you have high resolution perception, the fovea is actually very narrow. It's only about 2 degrees. So that's the first thing, is that your cone of vision is much smaller than it feels like, because it feels like you can see everything. 2 is that we don't actually have much visual memory. Right? So it feels like, you know, if I close my eyes, I can still sort of, I know everything is in the room. But in practice, we don't have memory for the visual sphere around us because we don't need it. Because if I want to access the image over there, I can just look, right? That's, our eyes swivel, and they do it unconsciously. And the brain is not very fast. It's highly parallel, but the clock rate is not very fast. Recall times tends to be in the hundreds of milliseconds. Well, if I've got a few hundred milliseconds, I might as well just look, okay? So we don't use memory, we use perception. And therefore, if we take information and render it visually, the normal perceptual mechanisms apply to the information we've just rendered. So, offload cognition to the perceptual system. So rather than thinking about all of this stuff, I can just look. And this is basically why visualization works. Now we can say a few more things about it. We can say, well, I can demonstrate to you that your visual system has a bunch of processing occurring in parallel at the preconscious level. So let's try this. Which one is different? Okay, no problem there. Which one is different? Okay, easy. You'd notice you didn't have to scan to do it. Which one is different? Okay, yeah, a little bit harder. You had to search. So that's interesting, isn't it? For some problems, you just know. And for some problems, you have to do a visual scan. So when we get above a certain threshold of complexity of the visual problem, we have to invoke cognitive methods. The point of data visualization is to present information in a way that doesn't require cognition. Okay, you want to swap cognition for perception. And so we can do experiments like this to find out what perception gets us. And the answer is quite a lot. So this idea where you don't have to search for something is called pop-out. And a great many things can trigger pop-out. So, for example, we don't have to think to know which line is longer or which is bigger. You saw orientation-based pop-out in the previous example. And it turns out there are quite a large number of visual channels. So depending how you count, there's, a dozen plus or minus different channels, which will trigger pop-out, and not just pop-out, but comparisons. So this has been extensively studied. And here's a list of the visual channels. In fact, 3 different lists. It's the same list. But it turns out that for communicating different types of information, different types of channels are more effective. So, for example, color, so let's say hue here, is not a particularly good channel for quantitative information. If you're trying to compare which value is bigger, like say you're trying to do a plot of GDP by year, color is not a great way to make fine comparisons, whereas position or even area or volume is pretty good for comparing quantities. On the other hand, for categories, hue is a great way to express categorical information, or texture. So there's a lot of research on how this works, and I'll try to sort of give you a sense of this very briefly. by grabbing one of the links in the syllabus. Here you go. 39 studies about perception in 30 minutes by my former AP colleague, Kennedy Elliott, who's now at the Washington Post. And what she's gone through here is she's gone through a bunch of studies about just perceptual experiments. So here's the idea. You can see some pictures of how this works. The way you do these experiments is you try to encode the same data in different channels. So in this case, you're looking at a ratio of two things. And you're saying, oh, let's try it as a direction. Let's try it as an angle. Let's try it as an area. And so, for example, you can see that it's much easier to read as a length than an angle, right? It's much harder to compare those two. And how you actually do this stuff is you typically do either reaction time or forced choice tests. So you give them a button, press A if the first one's bigger, or B if the second one's bigger. You see how long it takes them. Or you require them to press it in a really fast interval, a couple hundred milliseconds, 1 second or something, and you look at the error rate. So by these types of measures, you can measure what's the fastest way for people to do this. So Cleveland and McGill, that's just this paper we were just looking at. It's the classic one. This has been redone with crowdsourced stuff. And it just goes on and on and on. Here's comparisons of pie charts versus split line charts. Here's different types of pie charts. What else do we have here? Here's looking at comparing trends across multiple grouped bars. So if they didn't have these trend lines, how easy is it to see that category C is decreasing and category D is increasing? It just goes on and on and on. So we know here's experiments with tree visualizations. We know a huge amount about how people generally perceive this stuff most accurately. And if you're going to build visualizations, it's really good to familiarize yourself with these types of results. The other thing that you can do is use all of these channels together. So I'm going to play you this video since it's actually a really nice example of data visualization. So let's see. The late Hans Rosling.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health. Life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War. and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s, and in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up, Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you have seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
Ah, Hans.
It's nice to watch the day after the elections.
After the elections, yeah.
Like, oh, everything isn't so bad.
We lost Hans Rosling a couple years ago. It's too bad. He did a lot of really interesting work trying to get people to understand the trajectory of international development. Anyway, so there's an interactive visualization of this that you can play with. This is just a screenshot. What I want to talk about is the visual encoding design of this data. So how many visual channels are there here? And what are they?
Position, size, color.
Yeah, okay, so what's that?
Scale.
I think you mean that by size, same thing, yeah. Okay, so so position is actually two positions. We have the x and y axes. So what is each of them encoding?
Life expectancy, GDP,
Population.
And the color is? All right, so let's go back to this slide and think about this for a second. We've got positions, which are being used for, sure enough, two quantitative variables, the life expectancy and GDP per capita. We've got size, which is being used for a quantitative variable as well. So you can think of that, that's area really. So area isn't quite as good for encoding quantities as position, but they've also chosen a variable that isn't quite as important. They've chosen population. It's not as important to make fine population comparisons as it is to make fine life expectancy comparisons on this chart. And then they're using hue for a category. So in fact, the visualization design corresponds very closely with the experimental results on how people perceive things. And I would say there's actually one more channel here, which is time or motion. This chart, sort of the early experiments don't study motion, but there's a lot of research on, how well can we compare different rates of motion. If I show you an animation that lasts 5 seconds, can you remember what happened during that animation? And generally what they show is that it's hard to convey complex information in animations. You only remember very simple things. But in this case, all that you need to remember is that things went from the bottom left to upper right. If you need more complicated things, then sometimes what you'll see is trails, right? So if this moved from here to here, then you would have a trail like this. And that's one way to encode more information that way. So that's an introduction to the perceptual point of view of visualization design. Another way to think about visualization is like this, right? Make the salient features of the data visible without thinking. And to do that, you have to understand, as we've seen in these experiments, what it is you can see without thinking about it, and how to map those onto basic structures in the data. So this is an incomplete list that I put together of patterns in the data that it's possible to turn into very simple visual representations. So we've seen lots and lots of examples of clusters, and we'll see some more in our social network analysis. Clusters are a basic, possibly the most basic pattern in data, especially in multivariable data or high-dimensional data. And you definitely want a visualization algorithm that preserves clusters. But you can also look at things like the extent of the data, like the range of it, or find outliers, or look at more sophisticated patterns. So this is an incomplete list, of course. What other types of patterns in data can be turned into visual structures? Yeah, that's a good example. Like that's what a Venn diagram is.
Right.
Yeah. Yeah. Right, so you get to use motions, so you can turn temporal relationships into spatial relationships, so you can keep them as temporal relationships. What about, this one's kind of interesting. We're not really exploiting this, but we've got these little lines, right? So connectivity and paths. So that this was an example of that earlier. Sort of graph theoretic attributes can be turned into visualizations. When you start thinking about that, there's quite a lot of stuff that, with a little imagination, you can turn into visual encodings. One of the main things we are interested in when we're talking about analysis tasks is interactive visualizations. So most of the visualizations I've shown you are static. If you load up that Gapminder interactive, so this one, you can play with it a little bit, right? So you can select countries and you can change the time, and you can set the color and so forth. Interactive techniques are an enormous design space. This is a chart from a paper I quite like about visualization design, which tries to map out the space of where you should use interactive techniques versus automation. I also use this diagram when I need to talk to people who are used to automating everything. So, I'm talking to a Google engineer who's like, well, everything has to be run at scale, and so we have to have an algorithm that finds fake news on its own. Well, that only works if the task is very crisp, if you know exactly what it is you're trying to accomplish, and all of the information is in the computer, as opposed to the reporter's head from making phone calls or their interview notes in free text that hasn't been, entered into the system. Yeah.
I don't really understand the boxes for this. What are these? Is this talking about types of visualizations?
It's talking about when you should use, originally, yes, it was in the context of visualizations, but it's more broadly talking about when interactive techniques will work versus automated techniques. Computer scientists tend to like automated techniques because they don't have to think about those pesky humans.
Can you give an example?
Yeah, so let's take 10,000 PDFs of public records and find the story in them. So there have been techniques that try to take plain text and find stories. But it's much more effective to put the human into that process, because the human knows lots of things about what is interesting about those documents. One way to think about that is there's lots of information that is in the human's head, and the task, what they're trying to do, is not all that clear because there could be many different types of stories, right? So for that problem, you're kind of like around here in that space, which means that automated techniques are not a good fit. So it's just a way to think about how much automation versus how much assistance to human effort.
How does that apply to visualizations,
though? Well, interactive visualizations are squarely in this middle box, right? So one way to solve this problem of how do we investigate this huge pile of documents is to visualize the contents of them, as opposed to trying to do NLP and spit out the answer. Most visualizations are interactive. There's no point in making a picture that a human isn't going to look at. I now want to talk very briefly about visualization design. And so you're doing data viz in other classes, I imagine. Yes? No? Yeah, okay. You have a visualization class, or in the CS department, or here? Yeah. Okay. Do they talk about the same perceptual stuff? Okay. Visualization channels. Okay. Interesting. Okay, so it falls to me to talk about this stuff, I guess. In computer science, we tend to talk a lot about these inner two boxes. Visualization designers like publishing papers on visualization or algorithm design or some encoding technique. I'm going to show the probability of this thing on my Bayesian inference algorithm by color, and whatever it is. But this is another way to think about design, is that you sort of have to start from the outside in, starting with the domain problem. This is often a very complicated problem. So for example, the problem of investigating a huge pile of documents is not a particularly well-defined domain problem. Right? This is, and I've done a bunch of research on what I call the ethnography of data work. What is it that journalists actually do with documents? And you have to answer those questions before you can start talking about, this is how my topic model is going to work. Because topic model is all the way down at this level. So the idea is you work through from the outside in. Yeah.
What's the difference between domain problem categorization and data operation abstraction? So like the first one would be like what are we trying to design for?
Yeah, so what are you trying to solve? So an example in the investigative journalism context, this document set mining, not quite hypothetical example, is, okay, so I'm trying to find all places where it looked like a politician was taking money for a policy change. So that's the domain problem characterization, or one way of saying it. The data operation abstraction design is, okay, well, maybe the abstractions I want are people and payments. And then once you say, okay, settle on those abstractions, then you can go to the next level, which is the encoding or interactive techniques, and say something like, I'm going to show the people and payments in a graph, in a network. We'll see that later this class. And then the algorithm design is, okay, here's how I'm going to efficiently extract all of the people and places and render a graph and lay it out. But visualization, data visualization is more than just plotting data. So let's look at this New York Times piece on home runs. What else is here? The what?
Pictures of them.
Pictures, yeah, there's some people. What else?
There's a lot of text.
Yeah, there's a lot of annotation. What else do you notice here? Where does your eye go first?
Big number.
All right, the big number, and then where? Whoops. After the big number, where does it go? All right, this red line in its comparison to these other lines. So there's a bunch of stuff going on here. There's annotations, and there's visual hierarchy. Why does your eye go to the big number first?
Guys pointing at it.
Okay, why else?
The biggest.
The size, yeah. What else? Yeah, so position, size, other elements leading the eye towards it, the weight of the font. It's a very thick black font, as opposed to, so here's text which is lighter and smaller, so that's lower in the visual hierarchy. So there's all of this stuff that is not data visualization per se, but is all of the stuff around it that makes a visualization work. And there's titles too. So there's a very interesting piece of recent research that shows that by changing the title on the same chart, you can change what people remember. By changing the framing, right, you can have a chart that shows, a very moderate increase in crime rate over the last few years. And you can have a title that says, crime rate unchanged as police crack down. You can have a title that says, crime has increased as police crack down, or you can have a title that says, crime on a 10-year downward trend, just directing attention to a different range on the graph. You can really change what people remember by changing the words you put next to the pictures. So data does not speak for itself. That's, I think, one of the lessons of the data journalism program is, it is a narrative medium. And so doing a data visualization doesn't free you from getting the narrative right. This is a piece that I quite enjoyed when it came out. Oh dear, was this Flash? Oh no! Can I even... I wonder if this will load in any browser. This is the problem with reusing slides from last year, right? It's always the possibility that it'll break. Oh no. Here we go. Yeah, it was based on this. which came out a little bit earlier, and a lot of people enjoyed just these lines, this sort of animation like this. And what the New York Times did was they made this thing, which now I have a screenshot of, which showed the wind blowing to the right on the red dots and the left on the left dots, and of course the length of the vector is the size of the shift. So this was the 2012 midterms, which seems like a very long time ago now. And in fact, this is a general pattern in midterms. Generally, the president's party loses seats. That is the most common thing that happens with midterms.
Wasn't 2012 a general election year?
You're right, this is not the midterms, that was 2014. Okay, what I said about midterms is still true, but this was Obama's re-election, where there was a rightward shift, but Obama still won. And what I want to show you is the process of designing this visualization. So there used to be a blog called Charts and Things, which was one of Kevin Quealy's blog about creating these visualizations. Unfortunately, it's now only available through archive.org, which is another solution to my class materials keep disappearing problem. So it says it's based on the wind map, and you can see the sort of whiteboarding process that they went through here. It's not just that map, but it's they then break it down by the shift per state, and they break it down by different demographic groups as well. So here are Hispanic voters and young voters and women and so forth. So that was the original sketch, and it ended up here. And this is actually a nice little Tumblr. They had a lot of stuff on here. Let's see if we can get it through Internet Archive. You can learn how quite a few of these things were made. And it's not so much that the individual articles are super interesting. It's more, it's just neat to see the process. Yeah, I guess this is more work than it's worth right now. Here's another one that was from that. Here's another election thing where you can show how, I think it's how each state shifted to the left or the right over time. And you can see how it started out as just a quick visualization in R, and then some experiments with Sankey diagrams. This is called a Sankey diagram. And then here's the final piece. So when you make one of these fancy visualizations, it's not like it just pops, you just start typing it immediately. Right? There's a lot of sketching involved. And sketching not just like on whiteboards, but going through various iterations of attempts to do it with code. This is a really nice visualization as well. And it's a good example of narrative in a data visualization. So basically you just keep scrolling down here, right? So here's the observed pattern. Here's the change from the Earth orbit. So this is basically a data visualization of a NASA climate model. Here's solar variations. Here's volcanoes, which actually tend to be cooling because they block light. Here's all of it together. Here's deforestation, which also is slightly cooling. Here's ozone. Here's aerosols, which have actually quite a lot of cooling effect. And here's greenhouse gases. And then here's the model versus the observed, which, okay, so that is very interesting, but I'm going to make another comment here that you as data analysts should be worried about, which is, of course, the model matches the observed data. You don't publish a model on climate change that doesn't match the observed data, right? In fact, part of how we know that the model is working is it reproduces the reality. So all of the problems you have with machine learning where you don't want to peek at your training data apply to fitting physical models as well. What's the justification that the model is not overfitting? What types of justifications would NASA have for this?
Maybe it matches historical data as well.
So it matches historical data, but of course you don't choose models that don't match historical data.
Or like, I guess it matches future data.
That's what you hope. You hope to test your model by matching it against the future. And you can cheat that, right? So you can do like cross-validation style checking on your model where you train it on part of the sequence and see how well it matches on the parts it didn't see. The other big answer is robustness checks. If your model has various parameters, you look at how your model does if you vary those parameters, if you vary your assumptions, which is part of what generates these error bars, right? So this blue shaded region is the 95% CI, probably 95%. Yeah, there you go, 95% CI, it says there, for this model. And part of where that CI comes from is measurement error on the physical parameters that go into the model. And part of where it comes from is robustness checks on assumptions. So if we don't know exactly how much clouds contribute to global warming, or in this case global cooling, then we make some range of reasonable guesses, and that distribution of uncertainty gets incorporated into the model as model uncertainty. Anyway, I show this to you as an example of narrative visualization. I think there's one more. And here's everything together, and ta-da, it's a beautiful fit. Oh, and then I think it just goes back to the top. So this is a lot more than a chart, right? This is a pretty sophisticated interactive presentation. One of my favorite quotes about designing interactive visualizations is, if you're asking the user to click, the payoff better be huge. Is the payoff for clicking big enough here? Got a couple, yeah, mostly yeses around the room, yep.
I think it also goes in the direction of the internet, you know, rather than going,
the direction of the internet, yeah.
So I think, like, I don't know what it looks like on mobile, but I suspect that it would work well on mobile as well.
I think it does work here. I'm going to post it to Slack so you can try it.
You can actually just like change the width of the browser window, and if it's Chrome, it should like adjust for yeah, sure, you're right. Yeah.
Interesting. I think it just goes to static pictures on mobile.
Yeah.
Probably it just tries to avoid JavaScript.
Mm-hmm.
Yeah, and then it talks about where all of this came from. Oh, and this is what I was just talking about, these robustness checks. So here you go. It's robustness in several ways, right? There are 28 research groups around the world, and they've written 61 climate models. Each one is slightly different. But this is just one model. But this is how this science is done, actually. They very intentionally have a lot of different people using a lot of different models. And then they look at the aggregates of the models, which is not something we normally think about in terms of models. We normally think about, like, you know, measuring some value 10 times and averaging it to reduce the noise. But it's the same measurement process. Here, it's actually different groups with different methods. And there's experimental literature on, you know, does this actually work to have different people doing different estimates and take the median? Like, why should this work? And the answer is basically that it works because, you know, this throws out the extreme values, and you get straddling, where some values are above the true value and some are below, and they cancel each other out at least somewhat, and you get closer to the true value. Anyway. Wow, there's a lot of stuff there. Yeah, and here's actually the interpretation of the confidence interval. It's, as I said, they do a huge range of simulations, and then they pick the interval that 95% of them lie inside. So aside from the narrative structure of the visualization, which I think is very interesting, this really illustrates how the science translates into the data, right? It's not just you run a model, it's you actually run a suite of models, and you have all of the same problems that you have in machine learning with overfitting and validation and so forth. I guess one of the reasons I show you all of this is I want to try to dissuade you of the idea that data visualization is objective. So first of all, data isn't objective, and the simple way to see that is I can just mail you all of my favorite spreadsheets without column headers. Right? The names of the columns provide the crucial link between the world and the spreadsheet. And that's not objective. Those are facts that have to be reported out, right? Here's a chart that doesn't start at 0. It happens to be a chart from a technical paper comparing different ways of computing document similarity and showing that, this one, it compares the error relative to what humans think. I found this paper because I was very curious. If you do cosine similarity on a set of documents, how close does it match human ratings of similarity? And the answer is pretty closely, right? Like 80%. It's a reasonable approximation to how humans think about document similarity. Here's another chart that has become a little bit famous. This was presented to Congress, I think 3 years ago, talking about Planned Parenthood and okay, so what is the narrative in this chart? I don't think that that's what they're saying.
The narrative is that they're misusing resources that should be going to saving lives. That's maybe what they're
Yeah, generally they're saying Planned Parenthood does mostly abortions and not cancer. There's a bunch of weird stuff going on here. So I would say that this isn't actually a data visualization because it throws out, first of all, it throws out all the intervening years, but also it plots two things on a different scale. So, oh, do I have the link for this? Yeah. Here, let me show you the actual data that this is drawn from. Oh no. Wayback Machine to the rescue again. Let's see if we've got it. Yes. Okay. That's fine. Do we end up with, yeah, okay, here we go. This is what I want, so I will update my notes here. All right, so here was it being used in Congress, and here's the actual data, right? So if you get to choose the same scale on the left and the right, and you start at 0, it looks quite a bit different. And here's a more complete data set, which shows actually all the intervening data. Right? So Planned Parenthood mostly doesn't do abortions. They mostly do STI screening and contraception. So what is that saying? If you torture the data, you can make them say whatever you want. So you will find, if you go through this stuff, arguments about what fair data visualization is. So for example, you will find heated arguments about whether you should always start at 0 or not. Where do you all fall on that? Always start the y-axis at 0?
You better have a good reason if you're not doing it, but there's always exceptions. You should think about it if you're not starting.
Yeah. I don't know, I mean, there's a bunch of things we can talk about, but I don't know that there's any totally general rules for this stuff. But I think you can say that there is as much editorial choice that goes into graphing the data as there is in choosing the data itself. So again, the data do not speak for themselves. You have to make these choices. And here's another example of that. This was around the Obamacare debate. This was supposed to be a chart of how all of this stuff works together. This is the same chart, right? So you can lay out, again, the same information in different ways. And here's a close-up on that, which is a lot clearer. So, by the way, I'm certainly not saying that you shouldn't have a narrative in your data. If you don't have a narrative, why are you showing the data? Right? The data has to have a meaning. And so you have to choose the meaning that you want to display. That's part of being a journalist. It's just certain things can be intentionally misleading. All of the issues of objectivity and balance and so forth come into play. Just in the same way that it would be dishonest to leave out facts that are relevant to a story, it would be dishonest to leave out data that is relevant to the story. All right. So for the second part of this class, we're going to talk about social networks and journalism. And I'm going to try to ground it in at least a little bit of a sociological perspective. So just first a definition. We're talking about social networks. When I say social network, I don't mean Facebook. I mean nodes and edges, right? So it's a graph of people and connections between them. I haven't said what type of connections. So when we use social media data, we're talking about follow or friend relationships. These terms aren't completely standard, but often network analysis is used to mean there's only one type of relationship, and link analysis is used to discuss having many different types of relationships. And this is very common in big investigative projects. This difference becomes important when you talk about things like centrality algorithms, all of which are derived assuming there's only one type of connection. And link analysis ultimately grew up in law enforcement and intelligence. So journalism is sort of adapting many of these techniques. The entire reason this is interesting is because people act in groups. Or to put it another way, if I know something about person A, I can probably know something about person B as well, who's connected through a link. And you can sort of imagine all of the different ways that properties are transmitted through links. So for example, family ties are very strong. And following relationships on social media, those are the channels through which information flows or can flow. So you would expect that people who are, for example, follow the same person are exposed to the same type of information. And this applies basically in every sphere. There's a name for this, which is homophily. Friends with like, or as is sometimes said, birds of a feather flock together. Right? So people with whom you have a lot of ties, you're going to be similar to in some way. And that's basically why we do these analyses. It's an inferential method to transfer knowledge about one person into knowledge about people related to them. There's kind of two ways to do this analysis. So by the way, I'm talking about analysis of the structure of the network when I say social network analysis. I'm not talking about collecting all of the tweets about the election and doing text mining. I don't consider that social network analysis because if you do that, there is no use of the structure of the network. So I'm talking specifically about techniques where the structure of the network is used as data, right? It's part of the inferential method. And basically, the two ways people do this are visualize it and then use human interpretation, or apply an algorithm to compute something. In both cases, as we shall see, the results are highly contextual. In fact, this is one of the most contextual types of data analysis. You really can't just sort of read off the answer. You have to understand what it is you're looking at and who these people are. This is a pretty old idea. These are the earliest social network diagrams that I could find. Marino called them sociogram. Marino was a psychologist at Columbia who studied things like dorms where foster care children lived, fraternities and sororities, classes. And he started drawing these pictures. And his notation was, this is a diagram of, I think, a dorm. And he already is distinguishing between one-dimensional and two-dimensional links. So one dimension is just an arrow. Two-dimensional is a line with a bar between it. In other diagrams, it's actually a beautiful book. It's full of these hand-drawn pictures. In other diagrams, he has different colored links to indicate repulsion or dislike. So already in the 1930s, there was fairly sophisticated, very recognizably modern social network analysis. By hand, he got the data by going into these places and doing surveys. So just looking at this picture, who do you think is the class president? Anyone want to say the number?
5.
This one, right? Yeah, right. So that's interesting, right? We can learn something about the role of these people just by looking at the structure of the network. So this is the type of inference we're talking about. Rather than going into the visualization algorithms, I want to take a slight detour to a paper that I quite like. This is a paper about analyzing social networks from Facebook data. There is publicly available some very old Facebook data. It's anonymized, of course. I think it's really early. It's like 2006 or 7 or something. Facebook doesn't do this anymore. But there's various ways to get data like this. And the purpose of this paper is to show how to go from the image on the left, the hairball, to this image, which shows the actual underlying social communities. And it's based on a bunch of sociological assumptions. So what we've done here is we've cut out most of the links to reveal this diagram. And the way we do that is we look at triangles. And this is where this word Simmelian comes in. I think it was George Simmel. Yeah, it doesn't say his first name. I think his name is George Simmel. He was a late 19th century, early 20th century sociologist. So this is before any data was available, before people were drawing social network diagrams, really. And his theory of sociology was based on triangles. He made the following observation. He said, to study sociology, you have to study at least 3 people. because two people, when they act, so one person, obviously you can't study the social. Two people, when you study just dyads, these people aren't observed. Two people can have their own little world. There's no enforcement of the norms of society. So he thought that sociological theory needs to be built around how do two people interact when they're being watched? Hence, triangles. And triangles turn out to be extremely important structures in social network analysis. So graphs generally, like graph theory, is all concerned with edges, which is a 2-degree relation. Sociology is concerned with triangles. So let me give you an example of that. So I'm just going to draw a sort of pretty standard, like, friend graph. So let's say these are symmetric relationships of the, A is friends with B type. Now, there has been observed in sociology a simple predictive rule called triangle closure. And what triangle closure is if you have a triangle that is open, such as this triangle, if you watch these graphs over time, it is quite likely that the triangle will close. That is to say, you will add this edge. Okay? So think about the sociological mechanism there. What that says is that if I have two friends, it's quite likely that my two friends will meet. It's a very simple sociological observation. And it's highly predictive. And in fact, these open triangles, they are the basis of most social network person recommendation algorithms. So Facebook says you might also know. Well, how does it do that? The way it does that is it looks for the maximum number of unclosed triangles. So let's say this is me, and Facebook wants to recommend people to me. What it does is it looks for people who many of my friends know. Right? So there 3 of my friends know. And if I know them also, then it would close a bunch of triangles. It would close this triangle, it would close this triangle, and it would close, I guess that's it, because that's not a direct connection. Right? So one way to think about this is who is there many second-degree paths to? Another way to think about it is who do many of my friends know? But another way to think about it is how do I close the most triangles? So triangles as opposed to edges, so a set of 3 as opposed to a set of 2, are a fundamental way of thinking about social relationships that seems to have some sort of sociological reality, both theoretically, as proposed by Simbel 100 years ago, and in practice. And so this paper talks about different types of triangles, right? So if everybody is friends with everyone, in this case it's directed, you get a Simmelian triangle. Otherwise you get different types of triangles, right? So soul symmetric, so just these 2 people know each other and then this person is excluded, or just one person knows the other one. And this pruning algorithm, here's another example of what you can do with this algorithm in this extremely slowly rendering diagram. Can take these big hairballs and turn them into something much more easy to read, right? It finds the true strong ties. So it goes from the thing on the left to the thing on the right. And notice that without being told what dormitory people are in, it successfully groups people into dormitories, right? So it figures out who's actually friends with who and trims out all of these weaker edges. The way that the algorithm works is say it's trying to figure out if it should have an edge between A and B. Well, what it does is it looks at all of A's top friends, and the way it looks at the top friends, it asks how many triangles does it have in common. So someone is a top friend if you don't only have a link to it, but there's a mutual friend as well, right? So it looks for a triangle. Let's call this person C, which says that not only do I know it, but we have mutual friends. And it ranks these people who are part of triangles. It says, every person that I know, how many triangles am I involved in? In other words, how many mutual friends do I have with that person? And so let's say my close friends, or rather A's close friends. And then this is the number of triangles. So say I have friends in common. Number of friends in common. C, D, you have 4, E, you have 3, F, you have 2. And I'm actually going to order these because that's how the algorithm works. And then it takes some threshold. It says, the top 5. So this is my top 5 best friends as ranked by number of friends in common, on the assumption that the people for whom I have most friends in common are the closest. And then it does the same for B. So C, 3, H, 3, J, 2, E, 2, G, 1. Okay? And then what it asks is, how many of our closest friends are in common? So notice I start with binary data, you're friends or you're not. This algorithm really works. What it really wants is the strength of your tie to the friend, but it measures the strength of your tie if you only have binary data by calculating triangles, right? Friends in common. And then once you have these types of lists, then it asks how many people appear on both lists. So C appears on both lists, G appears on both lists, E appears on both lists. That's it. So then, because there are 3 people who appear on both lists, it says that the strength of the relationship between these two is 3. Right, so it's this sort of second order thing. First I figure out who are my close friends, and then I ask how many in my top 5 list or top n list are in common. And that gives me a weight of the strength of the connection between A and B. It says we have the same close friends. If we have the same close friends greater than some weight, let's say we have some threshold of 3, then we keep the edge, otherwise we throw it out. So using this triangle-based analysis, we can trim this hairball and get back a much smaller graph which is reflective of the sociological reality. In this case, everybody's living in a dorm together, and so you can see the dorm colors there. So this is a more complicated example at a different university, and what it has found is actually 2 different types of social groups. So on the left, so remember the algorithm doesn't have this information. On the left, they're colored by the dorm that they live in. And you can see that it's found some dorm structure here. So these people live in a dorm, and these people live in a dorm, and those people live in a dorm. But then you have this, right? These big multicolored nodes. And on the right, it's colored by year of graduation. So you can see that some of these are all the freshmen, right? So it is found sociologically real communities of multiple different types. So it's found dorm-based communities, and it's found year-based communities. And then it looks like there's some stuff that's truly mixed. So like when we start to get into here and here, these are communities that are neither year-based or dorm-based, but seem to have some sociological reality. I bet that's like people who like to go out to the same clubs or something, or are in the same class or something. I bet there's some variable which they actually have in common that we could find with a little more study. So this triangle idea is very powerful, and it seems to both theoretically and practically capture something about human social relations that appears in the data. Anyway, fun stuff to play around with. And each social network is going to be different. If you do this on Twitter, following somebody on Twitter probably means something different than friending them on Facebook. And Facebook has both verbs now, so I'm sure the follow networks and the friend networks will have different realities. Okay. I've shown you a lot of pictures of social networks today. Aside from the one that was drawn by hand, pretty much all of them are drawn by this algorithm called the force-directed layout. How many of you have seen this algorithm? Yeah, so it's a very simple idea. The idea is we throw nodes down randomly, and then we say that every edge is a spring that wants to push the nodes apart to a certain distance. So if they're closer than that, it pushes them apart. If they're farther than that, it pulls them together. And normally there's also a universal force, which is often called gravity, that just sort of pulls everything together. Oh, I'm sorry, no, it's the opposite. It's a global repulsive force that pushes everything apart, right? So you end up going from this to this, right? If you have this tetrahedral shape, it will get laid out like this. So the picture you get does depend on where you start, because you throw down randomly, and so you may get different shapes depending on your initialization. Also, you can use all kinds of different algorithms for laying things out. Here are a bunch of different layouts. Like, for example, this is a common visualization where you put everything in a circle and draw edges between them. These are actually all the same graph. And this is from a cute paper which investigates how the layout or the visualization of the graph, right? So technically it's exactly the same data, it's just drawn differently, how that influences our perception. So they ask people questions like, how many subgroups are there? Who's the most important people? And then they ask about sort of bridging roles, people who connect different parts of the graph, which, as we'll see, is important. So let's take a look at these for a second. How many subgroups are there in this diagram? Yeah, it could be 3, it could be 4, same here. Who's the most important person in this diagram? Or who are the important people? C? Why is C?
Seems to be connected to.
Because they're what?
Seems to be connected to most of the others.
Well, look at where C is here. So it turns out that the way you lay this stuff out has a big effect on inference. So just something to be warned about. As we'll see shortly, the primary analysis method in journalism is just looking at visualizations, but there is this question of whether the visualizations are really showing you reliable results. Nonetheless, force-directed layout is basically how everybody does it. It produces nice-looking pictures. It's, solves certain problems pretty well. And then there's the question of what we can learn from a graph. And there are many questions we can ask from a graph. One of the most common types of questions in sort of classical social network analysis is this idea of centrality, which is also influence or power, right? So we want to know who is the most important person here. Who's the boss? Who's the person I have to talk to? Who really made all of this happen? And you can just look at a visualization as we were just doing, or you can also compute metrics. Has anyone seen centrality metrics? Yeah, so this is what your homework is going to be about. So how could we compute who the most important people are in a graph? What type of metrics could we use? Any ideas? Degree? Node degree? Yep. That's called degree centrality. Any other ideas? Yeah, something about how it connects different groups. Yeah. There's actually a bunch of different ways, and I'm going to show you a few really quickly here. Because you should know this, because you'll run into it. So degree, and all of them sort of capture different ideas. So degree centrality is just number of edges. So I think of this as modeling a celebrity or a news hub, right? So who has the most followers? There's another kind called closeness centrality, and closeness centrality requires computing the average path length to every other node. So I compute the shortest path to every node. You've probably all seen shortest path algorithms. Yeah, okay. That's a computer science favorite. So what I do is I compute the average distance to every other node along the shortest path. So in this case, unsurprisingly, you end up with the one in the middle, just because the average distance is lower, right? So a real-world application of this idea is if you're getting on the subway and you don't know which end of the platform the exit is at, you should take the middle car, because the average distance is going to be lowest from the middle car. And this is a useful model if you're thinking about information flow or like flow of packages, like where should you put your warehouse to serve the whole country? Well, if you're only going to have one, it should be more or less in the middle of the country. It's the same type of logic. You can imagine that these are cities and these are road distances, driving distances, and so you put your warehouse, which has the shortest average distance. So this is called closeness. There's another one which is betweenness centrality, which is, again, you think about all of the shortest paths. So the set of shortest paths from every node to every other node. So maybe you compute it with Dijkstra's algorithm. I think that's one of my favorite algorithms in computer science. The all pairs shortest path n cubed algorithms. I won a programming competition with that one time, so of course I like it. But this kind of models introductions or transmission of some sort, right? So this is a map of the relationships, the intermarriages between the ruling families of Florence in Renaissance Italy. And you want to be the Medicis because if you're going to make introductions to marriage, they have to go through you, right? So you have the most control over how allegiance by marriage happens. Another example of this one is if you are thinking about networks of imports and exports, and you're levying tariffs for people to travel through your country, you want to be the country that everyone travels through. Right? This has strategic or military applications as well. This one is maybe a little less obvious. So this one is one answer to the problem. So all of the metrics that I've just shown have the following problem. Let's say we're talking about organized crime, and you have the mob boss here. And then you have, all of the other members of the mob in various places. But they don't get to talk to the capo, right? They get to talk to the secretary. Okay? And presumably to each other and so forth. And then the secretary talks to the capo. So all of the network analysis algorithms that we looked at, all of the centrality algorithms we've looked at so far, will say that the secretary is the most important person, and who's this guy, right? That person is not any higher than any of these other people, and maybe even lower. Eigenvector centrality says that your importance is not just who you can talk to, but whether you can talk to somebody important, right? So because the mob boss is close to the secretary and the secretary has very high centrality in betweenness, the mob boss will get a very high score. In this case, I suppose all of these other people will as well. But if we sort of back this off a few degrees, right, then this person is very important and these ones are not. But this person is still important because they can talk directly to the secretary. And so eigenvector centrality it's kind of the PageRank idea applied to network analysis. There's various ways of describing this, but one way to compute this is how likely you are to end up somewhere on a random walk. In fact, this was how PageRank was originally described. If I start at a web page and I start clicking through, following random links, a lot of those paths will end up at Wikipedia. So Wikipedia is really important. So this is the same sort of idea. If I start clicking through just following edges, and a lot of them will end up at the mob boss because a lot of them end up at the secretary, and once you're at the secretary, it's easy to get to the mob boss. Does anybody know why this is called eigenvector centrality? What's the relationship to eigenvectors here? Okay, so a little linear algebra tutorial. You should know this anyway, because this is how PageRank works. So the idea is we are looking for, and I'll use the technical language here, the stationary distribution of a random walk between pages, people. Which means, so I pick a random node, I start following random edges. The question is, how often do I end up at a particular node? And the stationary distribution is, say I throw 100 people into this graph and they all start walking around. From moment to moment, 70% of them will be at the most central node, and 30% or 20% will be here. And there's some distribution where after I wait a sufficiently long time and they're all well mixed, after everyone takes a step, that distribution will be the same. Does that make sense? It's the equilibrium distribution of random walkers. So the equilibrium distribution of randomly clicking about the web will have some high fraction of people on Wikipedia, just because although many people live Wikipedia in the same step, the same number of people arrive in the same step, and they'll have a much smaller fraction of people on the website for this course, because although some people link into it, basically all of the links go out and more of the links go out than in. So this was the idea. Now, to sort of complete this example, let's say we have a structure that looks like this, okay? And we need the idea of a graph structure represented as a matrix. Have you all seen this? An adjacency matrix? Okay, so here's the basic idea. We have some matrix, and you can think of this as the rows are from, and the columns are to, A, B, C, D, A, B, C, D. And you can always get from a point to itself in one step. So the diagonals are 1. And then you have a 1 if there's a connection between two edges, and 0 if there isn't. So in this case, I can go from A to B, C, D, 1, 1, 1. And I can go from B, C, D to A. So all those are 1s, and the rest are 0. And in particular, if the edges are bidirectional, then the graph is symmetric. If I have directionality, which I do for links, right? I can go from A to B but not B to A, then this becomes a 0. If I say that you have to move to a different spot, I can't stay on the same page, then the diagonals become 0. Okay? So this graph tells me how I can move around in one step. Now, fun fact, if I multiply this by a vector that tells me where I am now, so let's say I start on B, then what this does is this actually picks a column. You can see as you multiply through it, picks out a column of this matrix, right? So, yeah. And it says from B I can't get anywhere because I made that arrow one directional. But if I start instead at A, then it tells me where I can get to from A. So that would look like this. So this is standard matrix adjacency math. I have the adjacency matrix. When I multiply the adjacency matrix by a vector representing my current location, it tells me how fast I can get to various places. I can also think of this as a distribution, like a probability distribution. If I say that, you know, there's a 50% chance I'm on A and a 50% chance that I'm on B or D, and I take one step, well, then what I'm going to get is half this and half this. That's going to give me the probabilities that I end up at any other point on this matrix. So if I multiply this through, I get another vector. So let's call this matrix big A. Let's call this X. So AX equals where I can get in one step. If I take another step, well, this just gives me a vector of the distribution of where I am. AX or A squared X, 2 steps, and so forth. Okay? And in fact, you can do you can use this fact to do a shortest paths algorithm, right? You basically just keep on multiplying A by itself until it converges. You have to normalize at each step, but eventually what you're going to find is every term, if everything's reachable, then every term will get filled in, and you'll end up looking at all of the paths after 2 steps, 3 steps, 4 steps, 5 steps, 6 steps. So if I'm talking about an equilibrium distribution, remember the definition I gave earlier? If I start with people in some distribution, all of these nodes, and I take one step where everyone takes a random edge out, I end up with the same distribution. Well, what does that mean? So, well, let's say let's say there's some vector v equals v. Okay? So I take one step starting from some distribution v, and I end up at v. So this is the equilibrium distribution. And that's an eigenvector problem. Okay? You may recognize that as the definition of an eigenvector. In fact, it's a little different. I get a lambda in front of it, which is a scalar, so I multiply the vector by a scalar. But I can always set up the matrix just by scaling this, such that this equals 1. And that's just normalization of this matrix. So I can always get that. And now what I have is I'm looking for a distribution such that it doesn't change when everybody takes a step. And that's an eigenvector, right? That is exactly an eigenvector. So that's why this is called eigenvector centrality. So what I am doing is I am finding an importance or a centrality metric that I can assign to every node that says, after I take this one step where everybody gives a little bit of importance to everyone else. So in other words, instead of thinking about following a link, think about this in the social network sense of every step I give a little bit of my importance to everybody I'm connected to. And what is the equilibrium distribution for that, right? What is the distribution of importance where I get exactly the same importance out as I give out at every step? So I divide my importance and I send it all equally on each of my edges. But if I'm a very important person, well, that's because I'm connected to people who are sending a lot of importance to me. And that solves the president's advisor problem, right? The president doesn't talk to everybody directly, but the advisor does. So when the advisor sends out their importance, the president gets a huge fraction of it. And the president becomes an important person as well. So that is eigenvector centrality, and it's kind of a model for who you know, right? So maybe I'm not a celebrity, so I don't have a lot of connections, but I'm the producer for Lady Gaga, so I'm an important person too. So our next problem is, what does this all mean? Which centrality metric should we use? What do we do with this in journalism? And before we get into that, I want to talk about, just ask the question, let's say you walk into a small town and you're a reporter, right? The first thing you have to do is find out who is influential in that town. How do you actually do it? Because you're probably not going to start by analyzing social network data, although maybe. But let's say you don't have social network data for this town. What do you actually do? Like, let's bring it back to the real world here. How do you determine? Yeah.
Well, I would talk to reporters if they have time.
Okay.
A reporter who's been working there for a long time.
Uh-huh.
But I think that some methods that community organizers or like labor organizers use to map out the relationships in their communities that are purely qualitative, but like applying these methods to that I think would be really interesting. Like using power mapping, for example, which is a method that labor organizers use to assess the relationships that people have. And it's in a sense it's crowdsourced. It's usually done with a large amount of people in one physical space, just mapping out relationships and power structures.
Yeah, that is exactly right. So first of all, talking to the local reporter is always a good idea, but also just trying to figure out who's influential in society. And I want to show you an interesting document which I stumbled across a few years ago. This is from the 1970s. It was a handbook, again, it's linked from the syllabus, about development workers. We don't really send development workers into rural communities in the same way that we used to. But it was called Mapping the Community Power Structure. And here, look at this. Research has shown that successful community social action efforts depend on the appropriate involvement of key leaders in the community. So you have to find them. And here's how it suggests you go about it. So this is a wonderful little guidebook because it's a very practical reference to how power works in a community. And it suggests you do this thing called the reputational technique, which is, if we go to page 8, okay, it says you find knowledgeable people. You find a number of knowledgeables to be interviewed. Knowledgeables will be asked who they think are the community's power actors. So you go and ask people who's influential, and it tells you how many people to ask. And it says what you look for is people who appear on a lot of lists. So that's it, right? I think there's a nice resonance here with the Simmelian backbone method that we looked at earlier, right? You build these lists and you say who appears on lots of these lists. Yeah.
You say not much has changed in terms of communities and power structures and like.
Yeah, so why would that be?
Humans still behave the same way.
Yeah, right. You're talking about sociological and political reality, right? I think this method would have worked any time in the last 100,000 years. And will continue to work no matter what the internet does to us. I think, you know, there are two sets of insolvable problems, love and politics.
So like what would someone do practically? Say you're not going to a small town to be a reporter, but say you're in a new community and you have a topic and you're reporting, like where, so you talk to other reporters, so you like find community leaders.
Yeah, I mean, it's no different, right? So one of the questions you should be asking in any interview when you don't know the space well is, who else should I talk to? And eventually you find everybody gives you the same name, and you talk to that person, right? So you can think of this as a kind of degree centrality, right? You ask a bunch of people, you can think of sort of randomly sampling the network, and you get lists of names, and then you go talk to the people who a lot of people pointed to. So it's kind of a centrality algorithm. But I want to emphasize that you know, we've had a very mathematical presentation of centrality. It's a very sociological idea. It's very concrete. And really this concrete idea is much more important. I mean, you know, there's more to it, but here you go. Here's the question you're supposed to ask. I love the older slang. Who are the kingpins? Who can get things done? Who swing a big stick?
But I would say that like in a lot of places that's still applies.
Yeah, none of this has changed. You might use different slang, but that's about it. Okay, so that's linked from the syllabus. So this is really fun to read. And it's just basic field work, very similar to what reporters do. Which brings us to the very important issue of how does all of this centrality relate to the real world? You know, so this is a graphic from a Wall Street Journal story on insider trading. Unfortunately, it's offline now because the journal moved CMSs and lost all their interactives. That's twice today we've run into the problem of dying interactives. But it's about a very complicated insider trading case. And it was kind of fun. You could step through it and it would highlight different nodes and tell you what their involvement was. But you can tell just by looking at this that this is the central actor in the story. They have high degree centrality, they have high betweenness centrality. They're also placed in the center of the picture. Now, of course, they're going to be central to the story. The journalist is telling a particular story, so they get to choose the people to include and the links that are relevant. So remember, this is, if you just had the Facebook graph that included all these people, you may not get this person as central, because who knows if they're central in society. They're central once you pick a particular subset of people, which is a really important analytical point in graph analysis, that the answers you get are going to depend on what you sample. In any case, there's this idea that I've called journalism centrality. We want to know who's important to the story. And centrality metrics may or may not answer this question. In fact, centrality metrics are not used very often in practice. They have been used. So I wrote a paper called Network Analysis in Journalism, where I surveyed a bunch of famous stories and tried to break down what they did.
If you're just looking, like, I think a problem with that as applied to journalism would be that you don't want to find the central actor that everyone else has already interviewed, that everyone else is like I don't know, in journalism it seems like there's a lot of recycling of sources.
Mm-hmm.
And so how do you find someone who is central but maybe doesn't have?
It's a good question, and this is another problem with using centrality algorithms, is you usually already know who's central to the story. It's pretty rare that you don't have some idea of who the important person is in the story. Because if you've been reporting, then it's your beat, and so you know already from doing all of this previous work. But we're going to put that centrality aside for just a second. Your homework assignment is actually going to be about centrality. But I'm going to talk about something else that you can do with networks. So far we've talked about identifying and ranking individual people. Now we're going to talk about finding communities. And basically we're talking about finding clusters in the graph. Now, one of the ways to do this is just visualize it and just use your eyes. But just like you can look at a visualization and find centrality, or you can run an algorithm and find centrality, there are community finding algorithms. We're not going to spend too much time on this, but I'm just going to go quickly through a classic one so that you have some idea what these are about. So this is it, right? This is actually an old picture of my Facebook graph. There used to be a Facebook app that would draw this for you. And it's highlighted the different clusters for me, and they're actually like, you know, my San Francisco friends and my Hong Kong friends and some circus people that I used to hang out with and so forth. You know, pretty good job of finding this stuff. Yes?
Can I share an example? I can share this through Slack.
Yeah, put it on Slack. Meanwhile, I'm going to talk about this one. So this is, there's different ways of defining clusters because there's different ways of defining links. So this one is done with Amazon from the people who read this also read that. That's what each of these arrows means. And this was for the 2008 election. You can see that starting with a political book on the conservative and the liberal side, you get this these real clusters, right? It doesn't, this is sort of the filter bubble or echo chamber effect that you can see. But there's many different ways of defining community. So if you're, for example, if you're looking at Twitter, you can look at who follows who. That's the most obvious thing. But you can also draw an edge between two people if they both shared a particular link. So that's what I sometimes call that co-consumption. What was your example?
So it's a website.
Oh, Connected China. Yeah, I know this. Yeah, this is fascinating. So let's see.
Basically show you how like all of the politicians in China are connected to each other, also including their family members, and basically in their career paths, how do they interact with each other? It's a lot of information here.
Yeah, Reuters did this a few years ago based on a huge amount of research.
I think I saw this one like at least 3 or 4 years ago, but like over time they have added much more information. in your Slack.
It's yeah, it's called
Connected.
Connected China. Yeah, this one's kind of a fun one as well. It shows for various people the different stages of their career. So the previous and current premieres, for example.
I think it's just a color.
Yeah, it's not selectable. And every one of these is based on a news article. I don't know if they'll actually give us the links here, but how they did this is they had this whole database of relationships between people. Wow. It's quite a visualization. Well, okay, let's not get into China's government structure. I want to go back to the social power one. Yeah, this is the one that's most clearly a network analysis. And also most clearly not loading. Let's try that again. So I wonder if I can get the original links. If I click on this person, each of these links is an article. Connections. I don't think it'll show me the references here, but maybe here is where they are. No, this is just Reuters reporting. So they're not making the database exposed. And this was the brainchild of Red Schwa, who is now a data journalism exec at Reuters. And he has a blog. He's been writing about structured journalism for a very long time. And this is a sort of exhibit A. He had a team of reporters go through and just trace all this stuff out from public news reports. So they built this database of connections. There are different databases like this. We'll look at a few more. So for example, Little Sis. So you've heard of Big Brother? So I can look on a particular person. So let's search for a person, not Trump.
Andrew Gödel.
Andrew Cuomo. So there's the positions that he's had, and he's worked for these people, and he has this link to Martin Connor. Oh, I just get him. But for each of these things,
Also the network maps that people have contributed are pretty interesting. If you scroll down the page, it's on the right-hand menu side.
yeah, right.
A lot of journalists or just citizen researchers contribute really interesting network maps.
It's true. What I want right now, though, is I think this might be yeah, here we go. Each one of these is referenced. So here is the article link from which this one link comes through. So you can build up these networks just by analyzing public sources. And so, yeah, these maps that people make, right? And each of these, it says lobbying. And if I click on the link, it gives me the source for that one piece of data. Yeah, so Little Sis is pretty cool. Unfortunately, I don't know how much journalism actually comes out of this. I think it's more of a research tool.
I use it all the time.
You use it all the time?
Yeah, it's a great place to start.
They have an API.
Huh?
Do you know if they have an API?
No, they don't.
What do you use it for?
I use it as a first stop if I am researching an entity.
Mm-hmm.
I don't use it without any other sources. I don't know. I would never write something from Little Sis without fact checking it.
Mm-hmm.
But it's a great place to start.
Yeah, it's nice.
Especially for campaign donations and stuff.
Yeah, it's nice because it has all the sources.
Yeah.
It links to everything.
Who
Yeah.
can edit or contribute?
I'm not sure. It used to be anybody, but I think they have more editorial control now.
Wiley E. Coyote, I think, is
Oh,
a
won't
guy
tell me.
named Ziggy that works there. But yeah, Wiley E. Coyote is one that does a lot of the news someone that definitely works.
Like someone from Little Sis can only.
I think so, but anyone can make a map. Like if you have an account there, you can make like a network map using stuff.
So I wanted to move on because there's actually a video I want to show you. So let's do community detection, and then we'll go into how this stuff is actually used for reporting. Another way to define communities is who talks to who. This is the Enron email network map. Do you guys all know what this data set is?
Yeah.
So,
the
yeah, 500,000 emails, court-ordered release after the collapse of Enron Energy in 2002 over accounting scandals. You can get clusters through web link structure. This is an early example of trying to map the blogosphere in Iran. This is very cool. Or you can get clusters by where people go, right? You can see everybody who goes to a certain type of party because their location trails all end up at a particular club on Friday nights, right? Or a particular rave or something. We've talked a lot about clustering. You can use any of these cluster algorithms by defining similarity metrics on any of the attributes we just talked about. There is another one which is pretty standard. It's called modularity. You will see this in network analysis packages. And basically it works like this. It says, can we divide a set of nodes into two groups such that there's way fewer edges who cross that divide than if the edges were random. So it takes all the edges, imagines they're distributed randomly, and says, can I find a split such that I have many fewer edges than random and many more edges than random within each group? And so I'll just go through this pretty quickly. This is what this looks like. So this is just notation. I take the total number of edges here, which just sums the degrees and divides by 2. And then if I have the total number of edges, in a random graph, the expected number of edges between two nodes I and j is the product of their degrees divided by the number of edges. Hopefully you can convince yourself that that's right. The greater their degrees, the greater number of chances they have, and then the over 2m just normalizes. So now I know how many edges I would expect randomly. Now what I do is I take the adjacency matrix, which we just looked at, which tells me how many edges I actually have. I subtract off how many edges I would have randomly. I multiply by whether they're in the same group. So in other words, I count only the edges between the same group. And I define this thing Q, and if by summing over all pairs. And if Q is greater than 0, that means there are more edges within members of the group than I would expect if the edges are randomly distributed. So then the modularity algorithm tries to find G. It tries to find an assignment to groups such that Q is maximized. So that's it. That's the entire logic of the algorithm. It turns out that you can do eigenvector trickery here as well. I'm not going to get into it. But basically, you can solve this for a vector of group assignments. It is possible that there is no split that gives Q greater than 0, right? So there's no split you can do such that there are more edges within the groups than across the group, in which case you say there's only one community. Here's what this looks like. So we saw those books earlier. Here's what this looks like applied to that split. So the interesting thing here is that we only use the edge structure to do this analysis. We do not use, we know the political category of the book. That's the shape here, right? Circles are literal, squares are conservative, triangles are centrist. And it more or less reproduces the left-right split just on the graph structure, which tells you, again, that graph structure correlates to other things of interest. That's why we study graph structure. So there's a lot of ways of defining clusters. But this is a popular one, and the graph analysis tool you're going to use for your homework, which is Gephi, has this as an operation. And most graph analysis packages have it as well. Okay, now we get to how this is actually used in journalism. I wrote a paper on this a couple years ago. What I did is I went through the IRE tip sheet archives and found everything that talked about network analysis and categorized it. And here's some of the things that I found, right? So this is a visualization of the links between people in the Seattle art world. And so it's a nice interactive. You can click on each one and see who this person is. And the way they got this graph is they just went and interviewed people. They say, who else do you know? And then the reporter went through their interview transcripts and pulled out the edges. So the nodes are the people they interviewed and the edges are the who do you know. And then they colored it by, are they a gallery owner? Are they an artist? Are they a purchaser or whatever? Or a museum curator, and so on. So this is just sort of a basic, there's no network analysis in the algorithmic sense here. It's just a way to draw a picture of the scene. This is another very interesting case. This image never really appeared in the story. This was a story about juvenile car theft. And what they did is they got all the arrest records for juvenile car theft. And the edges are a co-arrest. So this edge here means that person and that person appear on an arrest record together. They were arrested at the same time. And they found these clusters. And then they had about 400 people in this central component. So they got a central component just to narrow it down. And they have the problem of who to go interview or investigate further. And this is one of the best uses of centrality measures that I know. They ranked people by centrality and then went and pulled additional data for those people. So they bought public records. So they can't do everybody because it's like $20 to pull this file for one person. So they wanted to focus on just the most interesting people. So they got extra data and interviewed more people who were central. So I went through like this and coded a lot of stories. And for each story I looked at, first of all, how did they use visualization? Was it just for reporting or did it appear in the story? Where did they get the data? Did they have to extract it from documents or did they just download the data? Did they run an algorithm and did they use a graph network database? So here's what we got. Visualizations appeared in most stories, but sometimes, in about half of them, they were also used for reporting, and you got an unpublished visualization like the one I just showed you. Actually running an algorithm was pretty rare. Mostly people are analyzing this through visualization. About 2/3 of the time or so, they can't just download the graph data. They have to scrape it from documents like we saw in the interview transcripts or public records or something. So then the question is why? Why are journalists not using graph analysis algorithms like centrality and modularity? What's the drawback here?
Might be difficult to interpret the results.
Yeah, it's difficult to interpret the results, but why is that?
What you value as the most important parameter of centrality could change depending on how you're looking at it?
Yeah. Broadly, the answer is context. That what the measures mean depends a lot about the details of the story. And by the time you do all of the reporting to get the details, you kind of know the answer anyway. That's pretty much what's happening. The other important reason is that you get heterogeneous networks, right? You do this kind of link analysis. You have these links like, worked for this person, went to school with, is family of, donated money. You can't really run centrality all in that because these algorithms all assume that every type of link is the same. So there's difficulty in interpreting this stuff. Also, you often don't have the whole network. Like if you're doing interviews and building out the network by talking to people, You can't run a network that tells you centrality until you've figured out that you have to talk to somebody. So that's why we don't see a lot of algorithmic graph analysis, but we do see a lot of visualizations. One of the uses of putting things in a graph and using visual tools is that you can put different types of information together. So this is a pretty classic one. We're combining 3 databases. Who Rick Perry made calls to, so he was running for Texas governor. Who donated to him and who got political appointments. And when you start to try to merge several different types of data, graph analysis becomes very interesting and useful. And what I'm going to show you now is a video. It's actually kind of an old video, but it's nice because it's very self-contained and not too long. And it's about a story on the tissue trade. ICIJ did this years ago. This is pre-Panama Papers. But it's a really good example of how you do graph analysis.
This is a story about companies that harvest human skin and bones and tendons and process them into medical implants. It's a booming market, giving human tissue a second life. You might say, what's wrong with that? In fact, you might know someone, like we do, who's walking around right now with a corpse tendon that repaired a busted knee. This is a legitimate industry, for the most part. These products can heal, even save lives. But I'm going to tell you 2 stories about how illegal tissue can feed that legal billion-dollar market. Here's the list of characters you'll be hearing about. A Florida company called RTI and its German subsidiary, Tütingen. A Ukrainian morgue named Nikolaev. A Russian coroner named Igor Alashenko. And a formal dental surgeon from Brooklyn, now a convicted felon named Michael Mastro Marino, who stole body parts, including from the corpse of the famous British commentator Alistair Cook. One last point before we get into the guts of the story. Our team looked at more than 200 companies. We talked to everyone from industry insiders and government officials to surgeons and convicted felons. We read through thousands of court documents, regulatory reports, corporate records, and internal company memos. Using a powerful analytical software called Palantir, we analyzed data on imports, inspections, infections, and accident reports filed with the Food and Drug Administration, the U.S. agency that oversees the human tissue trade. And we tried repeatedly to talk to the company that ended up being the focus of our investigation, but executives wouldn't talk to us or respond to written questions. So here's our story. There's this company called RTI Biologics, which started out as a nonprofit division of the University of Florida. Since breaking away, it has become one of the world's largest publicly traded for-profit tissue processors. As we dug into this global trade, we started to see a pattern. RTI and its German subsidiary Tütingen have repeatedly obtained tissue from suppliers that were later investigated for allegedly stealing human parts. First, let's go to Ukraine. This February, a few months into our research, authorities raided a morgue in the southern city of Mykolaiv. We talked to investigators there. They suspect body parts were stolen from cadavers brought in for autopsy. They told us signatures were forged to make it seem like families had given their consent. The Ukrainian investigators said tissue might have been taken illegally from as many as half the bodies that passed through the morgue. During the raid, police seized autopsy reports written in English, lab results apparently destined for Tütingen, and bottles of human tissue labeled Tütingen, made in Germany. But one thing really caught their eye: an envelope stuffed with cash labeled NIK1. That's the U.S. government's abbreviation for the Nikolaev morgue. See, the morgue was registered as a tissue bank with the FDA. What's interesting is the phone number listed for that morgue was identical to 24 other Ukrainian morgues also registered in the U.S. And what's more, when we called that number, we reached an automated system for Tütingen, which makes medical implants out of human tissue. In early 2008, Tütingen merged with RTI. Remember, that's the big American for-profit tissue processor. Back in the 90s, Tutagen got its tissue from suppliers in places like Estonia, Latvia, Czech Republic, and Hungary, where tissue can be taken without consent unless a donor opts out while he's still alive. Families complained in some cases. Police launched investigations, but they didn't go anywhere. We got a hold of internal records that show Tutagen has been getting tissue from Ukraine for more than a decade and supplying RTI. The company appears to work through a middleman there, a Russian coroner named Igor Alashenko. Until the raid in February, Alashenko was director of BioImplant, a company owned by the Ukrainian Ministry of Health, which collected the tissue from regional morgues to send to Tutagen. Internal records show Tutagen had real problems doing business with Alashenko. In a 2002 memo marked "strictly confidential" with 4 exclamation points, Tutagen executives urged an exit strategy from Ukraine. They wrote that a middleman, believed to be Alashenko, kept demanding more money, and they didn't know what happened to the money they sent him to pay the morgues. Despite these misgivings, Tutagen didn't pull out of Ukraine. Instead, the company expanded its regional network. Over the years, Ukrainian authorities have investigated 2 other morgues that supply Tutagen for allegedly stealing tissue, bullying families, and forging consents. No one has ever been convicted. As for Alashenko, local news reports say he left Ukraine following the February raid. Neither police nor health officials will tell us where he went. So where are we today? RTI doesn't import its Ukrainian tissue through Germany anymore. The Ukrainian tissue bank BioImplant is exporting directly to the United States. But foreign tissue is still a small part of RTI's supply chain. Like other big players in the industry, RTI actually gets most of its tissue in the U.S. But U.S. law hasn't kept up with this rapidly evolving industry. And that brings us to our second story. Here at home, RTI operates a nonprofit called RTI Donor Services, which directly recovers tissue from American cadavers. RTI has also contracted with tissue banks in 23 states. One of those suppliers was New Jersey-based Biomedical Tissue Services. It was run by a former dental surgeon from Brooklyn, Michael Mastromarino. RTI started working with Mastromarino in 2002, but got nervous when staff complained that he was verbally abusive and had ties to organized crime. So RTI hired a law firm to run a background check. And here's what the firm advised. The good doctor has been on Santa's naughty list for quite some time. I would strongly encourage you not to do business with someone that has this kind of resume. Instead, RTI drew up a new contract with Biomedical Tissue Services. In place of Mastromarino's name was that of his newly licensed off-site medical director. RTI continued to work with the company and Mastromarino as their main contact until 2005. That's when the company found out what he had really been up to for the last 3 years. From funeral homes in the Northeast, Mastromarino stole body parts, some infected with cancer, hepatitis, or HIV, from more than 1,000 corpses. One source of tissue was the body of Alistair Cook, that famous British broadcaster and host of Masterpiece Theatre. He died at 95 of lung cancer. But his death certificate was altered, and then his cancer-ridden tissue was sold for $11,000. There were massive recalls. 5 companies pulled back a total of 25,000 products made from the human tissue Mastromarino supplied. And police got on his case. He's now serving time at a maximum security prison after pleading guilty to conspiracy and body theft. And the families of his victims filed a lawsuit against RTI alleging negligence. That case goes to trial this October in New York. When we started looking through court files and started talking to people, we realized that neither companies nor the FDA had ever tried to verify whether consent was actually given. No one cross-checked the files until after the industry was alerted to a pending criminal investigation. So what's the bottom line here? Why should we care? Well, you should care because regulations are ineffective. Given the enormous profits that can be made in the industry, it's shockingly easy to get into. Just fill out a 1-page form on the FDA website and you're in business, according to those who have done it. You can harvest tissue yourself. You can distribute it on the open market. You don't even have to be inspected. In fact, according to our analysis of FDA data, only about 40% of tissue banks in operation today show any record of being inspected by the agency. So why do we need this fancy software to figure out the story? Well, you can see how complicated all the networks can be. These companies and their operations stitch an intricate network across the globe. But those connections are buried in paperwork and data sets. Ultimately, we uploaded more than 1 million companies, people, document, and events into the system. So to sum up, the human tissue trade is a perfect example of demand outstripping regulation. It's not surprising that some unscrupulous characters, sensing massive profits, may have latched on to an otherwise legitimate industry. And that's a fact the FDA and Congress have overlooked.
So there's an older example. A more recent example is the Panama Papers, which there's lots of material online and talks about how graph analysis was used. They put everything into a Neo4j database and then visualized it with Lincurious, which is this tool. One of the things that is interesting about this is that there are a lot of specific challenges, right? So here's the idea, is you throw everything into a database, and then you can, because a graph is a very flexible representation, you can represent almost anything you want. So anything in a relational database, you could put into a graph, and then you can merge them and find paths and do these visualizations. There's a number of issues, one of which is that the structured data in the Panama Papers was only a small part of it. Well, a big part, but the minority part. So documents, emails, and PDFs were a much bigger part. So you have to figure out how to turn that stuff into graphs. Perhaps the most obvious way to turn it into graphs is to do entity recognition on the documents. However, entity recognition, commercial entity recognition has recall of only about 70%. Because it's tuned off as against precision, right? It doesn't want false positives, which means that commercial tools are not going to pull out all of the entities. And so journalists have had to do a lot of work to tune entity recognition for the investigative workflow, because you would rather have a bunch of leads that don't pan out than to miss something. The other big problem is record linkage. So if you have n data sets, you might have n copies of the same entity, in this case a company. And here you can tell they're the same, right? Like look at the address, it's the same thing. IFG House, 15 Union Street, Haifa, Jersey. They're just written differently. You can often have the computer find them. When you do have a computer find records to link, you don't want them to actually collapse it down to one node because it could be wrong. So instead, the preferred technique is a soft record linkage, which is you add another edge. So in this case, the relation is called has similar name and address as. So you throw all these data sets into the graph, you apply some similarity algorithm, and here machine learning actually works quite well to try to figure out which are the same entities, but you don't merge edges or merge nodes. You add a notation that says we think they're the same, because then later a human is going to have to check it. The reason for that is you can't ever accuse somebody of wrongdoing based on the output of a model. Anytime you're going to make a public claim of wrongdoing, you have to check every step of that by hand. Otherwise, you are at risk of libel, and in particular negligence for libel. The system that I would like to see for doing this, it's up in sort of prototype form in a number of organizations, including ICRJ and OCCRP. I'm going to show you in a minute a slide of what I wish we had that tries to solve some of these problems, right? It's not as simple as just throwing everything into a database and then running a graph algorithm. For a variety of reasons, record linkage is a major problem. Another one is that the graphs that reporters use are not data visualizations. So here's part of an investigation into Trump's business that we did here at this school a couple years ago. This is a hand-built map. It's done in a program called CMAP. Journalists have been doing this for decades. It's not a data visualization. These things are in a database, but we're not just plotting the result of a query. We're choosing which things are important, and we're setting a layout based on, well, obviously we're focused on Bayrock, which a lot of journalists have been looking into. Here's that Wall Street Journal story again, and you can actually step through this. This is all hand built. What I'd like to see is a system that is based on the graph database. So, if you run some query, you get all of this stuff, but lets you pick which ones you want, right? I want it to allow you to build these. They're not data visualizations, so I'm calling them maps. It builds maps by searching in the database and adding one node at a time, which is kind of what Lincurious does. This is the Lincurious interface on the right. And so when you see these pictures with the Panama Papers, that's how they were built. They were hand built based on expanding out nodes and people of interest. The system that I'd ultimately like to see is this. You combine both structured and unstructured data, which goes through entity recognition, to build a huge graph database, including provenance information and multiple copies when you have a thing in multiple sources. Then you do record linkage to generate these individual maps which are specific to the story you're investigating, right? So the key thing here is these maps are not data visualizations. They are hand-built with computer assistance for record linkage. And in particular, if you learn something interesting, you should be able to just use this interface and click on it and say, oh, I want to add a new node that then goes back into the central data store. So people are starting to build systems like this. I know of at least 3 efforts to build something which looks like this. So this is really the future of high-end cross-border investigative journalism, is these types of pipelines and graph data stores. Okay, your homework will be up shortly. You are going to run multiple centrality metrics on the Les Mis data set. So how many of you know the story of Les Miserables? Have seen the musical or the movie? Yeah, if you haven't, I'm afraid you'll just have to Wikipedia it for the plot. What I'm looking for, so it's a graph which has all the characters and how many chapters they co-occur in. You're going to load that up into Gephi, run different centrality algorithms. What I'm looking for is an analysis of how well the different centrality algorithms capture the plot of the story, right? So again, the fundamental questions in this course are always about the relationship between the mathematics and the world. So this is exactly that problem. Tell me what the centrality metrics tell you and whether it matches the story. All right, I will see you all next week.